All right, here we go. All right, so integral of what?
Integral of 1 minus 13 secant t over cosine of t minus 13.
Oh, so I need to make this a little bit bigger. All over?
Cosine of t minus 13.
Like that? Well, okay. What I might be inclined to do is, let's see. Yeah. Multiply by cosine of t. That is the suggestion. Okay, so what happens if I do that? We'll see if this gets us some traction. I have another idea if this doesn't work. Okay. So what's that going to give me upstairs? Okay. Oops. Cosine of t minus, because secant is 1 over cosine. To be cosine of t minus 13. Okay. And then on the bottom, it would be cosine of t. So what would it be? Yeah, so it'd be cosine of t times, how convenient. What's going to happen to the cosine of t minus 13s? They cancel. And what are you left with? Integral of 1 over cosine, which is just the integral of secant. And now we're in business. You actually know that antiderivative straight up, right? It's just logarithm absolute value of secant t plus tangent t, right? What's the constant? Yes. Yeah, probably. Yeah. Because secant times cosine is just 1. Right. So the top, if you multiply top and bottom by secant, the same thing would happen, but you would have 1 minus 13 secant of t on the bottom, and then 1 minus 13 secant of t upstairs times secant of t. So those 1 minus 13 secant of t's would cancel. That's another way you could do that. Does that make sense? Okay. Other questions? Other questions? Okay. Wanted to start with an example here. So let's see. I'm going to go over to another page. Okay. So let's do this one. Integral of 3x minus 7 over x squared minus 3x minus 4 dx. It's like our favorite. It's like our favorite quadratic on the bottom right there. Yes, quadratic is a second degree polynomial. We were dealing with that one yesterday, and here it's making an appearance again. Okay. So what would be the first step in trying to pull this off? Yeah, so how does the denominator factor? That's right, x minus 4, x plus 1. Okay. We say to ourselves, all right, I'd like to break this thing up. Okay. This is slightly different than what we had last time. So let's kind of see it. So the thing is, we have 3x minus 7 over x minus 4, x plus 1. We want to do this partial fraction decomposition, which is kind of like unadding fractions, yes? Sort of like an unadding of fractions, where what I mean by that is, you know, usually when you add fractions together, you try to find a common denominator so that you get one thing. But here we're trying to go backwards, which is a little bit trickier. So in this case, I would have something over x minus 4, and I would have something else over x plus 1. Okay, what do I put upstairs? Is it, yeah, just a number and another number. And you might say to yourself, well, how does putting a number up there going to account for the fact that I need to have an x term in the end? Well, think about it. If there's just a number here and a number here, if I were to add those two fractions together, and incidentally, I mean for these things to be numbers, okay, that's a number and that's a number, okay? If I have these two numbers, if I were to add these fractions together, I would have to find a common denominator, and I would have to multiply a by x plus 1. And I would have to multiply b by x minus 4. So when I combine those things, I would end up with an x term. Does that make sense? There would be like an ax and a bx that I could add together and get an x term. And that's something that tends to bother students. They think when they first see this, they're like, how am I going to manufacture an x term from the partial fraction decomposition? But if you think about going back, you can kind of see how that would happen. Okay, so this is legitimate. The thing I suggested to you was to clear denominators. So what are we going to multiply everything by? Yeah, so you multiply by x minus 4 times x plus 1. And that clears denominators, right? So that's going to go through to everything. We end up with 3x minus 7, right? Because if I multiply that by the left-hand side, it completely cancels. 3x minus 7 equals a times x plus 1 plus b times x minus 4, okay? And this is where we start to have options. You can either use the so-called plug-in method, or you can use the comparison of coefficient method, yes? Okay, let's kind of see both versions of that. At least in these initial stages, it's good to do that. So here's the plug-in method. So what sorts of things do you think I'm going to plug in? Sure, right? If I plug in x equal to minus 1, look, the left-hand side, if I plug in x equal to minus 1, I end up with like negative 10. See what I mean? Yeah? Because negative 1 times 3 is negative 3 minus 7 is negative 10. If I plug in negative 1 on the right-hand side, the first summand dies, but the second summand survives. Okay? Isn't that going to be minus 5b? So what do we get for b? B is equal to 2. Exactly right. Okay. Okay. Secondly, I'm going to, just so I can save some room, I'm going to write it off to the right here. X equal to 4 is a good choice, because that kills off the second summand that involves b. If I plug 4 into the left-hand side, I have 3 times 4, which is 12, minus 7, which is 5. You get 5 equals what? 5a? Okay, interesting. Which means that a equals 1. Exactly right. Okay. Now, what about the comparison of coefficient method? Okay, so the coefficient method. Well, to do that, I basically need to go back up here and distribute some things. Like I would need to distribute A here and B here. See what I'm saying? and sort out what that gives me once I do that. So first of all, it would be AX plus BX. Do you see what I'm saying? Which is all told is like A plus B times X. And what would I have for the constant term? A minus 4B. Do you see that? So this 3 that's sitting in front of this X, I would have to pair that off with A plus B. After all, that's what's sitting in front of X. Okay? And secondly, and this is where you have to be careful, I have a -7 here, right? I have a plus over here, right? You almost want to think of this as plus -7, right? Plus -7. So this -7 needs to be paired off with this constant term over here, okay? So what do we get? A plus B has to be, what's A plus B equal? Yeah, 3. And A minus 4B, which is the constant term, that has to equal -7. Great. Now, let me label these things. Maybe I call this guy 1. I want to just do something slightly different from what I did last time. Maybe I call the first one equation 1 and the second one equation 2. What would happen if I subtracted 2 from 1? So if I go 1 minus 2, what would I get? Yeah, do you see that? So the A's would cancel, and it would be B minus -4B. So what would I get? How many B's? Well, the A's would cancel. I would get B minus -4B, which is 5B. You see what I'm saying? What about on the right-hand side? 3 minus -7 is not -10. 3 minus -7 is +10. Okay, all I'm doing is I'm taking the first equation minus the second. The left-hand side, the A's go away and you get 5 B's. The right-hand side, you get 3 minus -7, which is +10. So what's B? B is 2, once again. And then I don't really have to do anything else fancy. I could simply take this B and put it right there. And I immediately know what A is, right? Since A plus 3, or since A plus B is 3, right? And I could just put B right there. I immediately know that A is what? A is 1. Got it? And now we're ready to finish this thing. So let's see. Let me go over here. The integral of 3x minus 7 over x squared minus 3x minus 4 dx. This is equal to the integral of 3x minus 7 over x minus 4, x plus 1. I think I put the a over x minus 4, didn't I? It was the integral of a over x minus 4 plus b over x plus 1 dx. And you say to yourself, all right, we know what a and b are. What was a? All right, and b was 2 from our work over there. So this is the integral of 1 over x minus 4 plus 2 over x plus 1. Unless you doubt, like lest you say, hey, I don't know about this. I don't feel so comfortable with my numbers. What could you always do? You could just add them together. Does that make sense? You could literally add them together and make sure you get back to that 3x minus 7. So you would multiply 1 by x plus 1, right? You would multiply 1 by x plus 1 and 2 by x minus 4. So what I'm saying is, just going off to the side here, you could say, I mean, look, this is, I'm not doing this to kind of solve the problem. This problem's basically done, but I'm just checking my work right now, yes? This is just a check, okay? This would be 1 times x plus 1 plus 2 times x minus 4 all over x minus 4x plus 1 dx, okay? And guess what this is right here? What do you get? 3x minus 7. Check, right? Everything seems to check out. But going back over here, I'm ready to roll in terms of finding the integral of this. This would be the logarithm of what? Yeah, absolute value x minus 4 plus 2 logarithms absolute value of x plus 1 plus a constant. Now, let me reiterate that that is the answer, right? So we're done at this point. There are ways to simplify this, though. You could say, you could like bring this, let me just say, you could bring this power up here if you wanted to, right? That's at that 2. You could, and then after you do that, you have a sum of 2 logarithms. So you write it as the product of 2 logs. That might be useful later on if you didn't want to have to work with this gnarly sum of 2 logarithms. You could write it as a single logarithm. So you could say, all right, this is just a logarithm of the absolute value of x minus 4 times what? Oops. Absolute value of x minus 4 times x plus 1 squared. We don't even really need the absolute values on that since it's being squared, okay? Yeah, but you don't have to necessarily do that last step. That's just something that would be convenient for other purposes, potentially. Like in differential equations, doing what I just did is actually fairly needful at times. Yeah.
Would it be all under 1 absolute value, or would it be the absolute value of x minus 4 times the absolute value of x? So in other words, when you multiply the 2 logs together, what's inside those, do you keep them as separate absolute values, or do you?
Well, yeah, if necessary. I mean, you could just combine them under 1 absolute value. The only reason I wrote it the way I did is because it's being squared. If it was raised to the 3rd power, for instance, then I'd have to start worrying about pluses and minuses. So I'd better keep the absolute values in that case. Make sense? But yeah, I mean, that would be fine. Other questions? Well, I want to share. I'm going to share my screen here. Okay. Okay, and I'm going to go from right here. Okay, I'm going to close this down. All right, so here's kind of some steps for, I like to call it, just because it's not as technical of language, we're basically unadding fractions. That makes sense? That's the essence of what we're doing. So something like partial fraction decomposition sounds like you're some kind of mathematical elitist or something, right? But it is the technical term. You do want to know it. But what we're basically doing is unadding fractions. We're doing the reverse of what we have done up until now. Okay? So here's kind of the steps. Like, again, we start with some numerator polynomial over denominator polynomial. Divide if improper. So what do I mean by that? Divide if improper. If the power on top is higher than the power on the bottom, the initial step is always to divide so that you get something that's going to be easy to integrate. And then what remains is going to be a numerator whose degree is smaller than the degree of the denominator. Yes? So that way, moving forward, we can always assume the degree of the top is always smaller than the degree of the bottom. Step 2 is to factor the denominator completely into linear and irreducible quadratic factors. Now, again, sounds like I'm some kind of mathematical elitist here using terms like quadratic. What does that mean? Right, a polynomial that has squared terms. There are going to be times where you will have unfactorizable quadratic terms. Does that make sense? you will have things like x squared plus 1 that simply cannot be factored. Now, if you're willing to use complex numbers, like use the square root of I equals square root of minus 1, you could have nothing but linear factors in the end. It would be completely nothing but linear factors. And by the way, I still sound like a mathematical elitist. A linear factor is a polynomial of degree 1, okay? Or 0, right? I mean, like even a constant term is considered a line, yes? Okay. For each linear factor of the form ax plus b to the n, okay, this is something that's slightly new. For each linear factor of the form ax plus b raised to the power n, include in your partial fractions decomposition terms of that form. So look, you have the thing raised to the first power, a number over the thing raised to the first power, plus a number over the thing raised to the second power, plus a number over the thing raised to the third power, plus dot, 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 plus a number. All of those capital A's are numbers. Do you know what I'm saying? Over the same linear factor raised to the nth power. Now, that looks confusing, and you're thinking, you might be thinking, what on earth is that even saying? But let me give you a quick example, okay? Okay, so what this means is if I had something like, let me go over into here. If I had something like this, so suppose I had something like, 5 over 2x plus 1 cubed. How would I, sorry, and this was times, let me see, multiplied by something else like x minus 1 or something, okay? Then how would I represent this? Help me out here. Yeah, a over x minus 1, and I'm basically done with that part now. Now I have to deal with the other junk. Know what I'm saying? Okay? So what would I do with that? B over 2x plus 1 plus, and then you have to crawl your way up to the power 3, okay? Plus c over 2x plus 1 squared. Am I done yet? Plus d over what? 2x plus 1 cubed. And you might say, what? Well, here's why. Like, think about it. If I were to bring this to a common denominator, okay, so first of all, what is the degree of the bottom of this thing, okay? So what is the degree of the bottom? What's the degree of this? Degree is equal to, if I were to multiply all that junk out, what would the degree of the bottom be? It would be the degree would be 4. The highest power of x would be 4. So potentially upstairs, okay, let me just make this slightly more complicated. I could have something all the way up to degree 3. Does that make sense? So I could have some other stuff here. I could have like, x squared plus 2x plus 5 or something. Does that make sense? It could look like that. Okay? So this stuff up here would be of degree less than or equal to 3, okay? I could have anything up to degree 3. If it was degree 4, then I have not done my job, right? I should have done polynomial division to begin with. But upstairs, it's of degree equal to or less than 3. So in my decomposition, I have to allow for the possibility of degree up to 3. You hear what I'm saying here? So think about this. Does this do it? Think about this. What would I have to multiply a by to bring it to a common denominator? Now I'm re-adding the fractions just to make sure I've done this rightly. What would I have to multiply a by? 2x plus 1 to the third. Ooh, there's a third power of x, yes. Plus, what would I have to multiply b by? 2x plus 1 squared times x minus 1. You see what's going on here? So that b is going to have a potential power of 3 next to it. Does that make sense? B could be 0, by the way. It might just go away once we kind of sort everything out. Okay? And what about C? 2x plus 1 times x minus 1. So do you see what's happening here? I have kind of given myself the ability to have a cubic term, a squared term potentially, and I'm telling you an x term, right? Because like what would I have to multiply d by? Just x minus 1. And all of this junk would be over the denominator, right? So x minus 1, 2x plus 1 cubed, right? So look at that. All that junk upstairs clearly allows for the possibility of a polynomial of degree at most 3. Does that make sense? Okay. So this is indeed sort of a proper breakdown of this thing. Yeah. Just wanted to make sure we were kind of clear on that. And by the way, each of those, I am telling you, we know how to do them. We know how to do this guy, right? A is just a number. Yeah, that's easy to deal with. That's going to be like a times logarithm absolute value of x minus 1 if I integrated it. Yes. I know how to do this. That's slightly more complicated because it's a 2x, but it's still going to be just 1/2 logarithm absolute value at the bottom. Yes. How would I deal with this guy? Yeah, just do a u substitution. Put u equal to 2x plus 1. Then that would just be like basically u to the -2, and you know how to do that. Yeah? So check. What about the fourth guy? U sub again. It's going to be basically like u to the -3, and you would know how to deal with that guy. Okay? So the breakdown of this thing works out nicely. What would happen? What would have happened here? Okay, just to make sure we're all on the same page. What would have happened here? So x squared plus 2x plus 5 over, what if this would have been like x minus 1 squared, 2x plus 1 cubed? What would I have done then? Yeah.
Well, I was just going to ask for the original. Is this one of those situations where plug-in method is basically impossible to do?
The plug-in method would work. Like for instance, if okay, check it out. If I plugged in x equal to 1, it would kill the b, c, and d terms. So you would be able to get some stuff. Does that make sense? But probably not everything. And by the way, you don't have to, here's a little secret. You don't necessarily have to plug stuff in that's going to kill everything. It's helpful to do that. But then when you run out of stuff to plug in that's going to kill stuff, for instance, like I could also plug in x equal to -1/2, right? And that would kill a lot of stuff. But then we're like, oh man, I don't have other things to plug in. Well, just plug in other convenient things, like 0. Because once you've plugged in 2 things, you're going to know the values of some of these variables, right? You might know like what D is maybe and what A is, but you're like, what's B and C? I don't know. But you already have those done. All you need is, you know, some kind of equations that B and C have to satisfy. And you can do that by plugging in other numbers that are convenient. Or you could just compare coefficients and come up with your equations that way. So what would the form of this be? I don't want to rewrite the entire thing. Wouldn't it just be exactly the same? Yeah. Right. So same plus there would be one additional term. What would it be? B over X or E. I'll use E. Okay. Sorry. Capital E over X minus 1 squared. Does that make sense? So it'd be exactly the same, but you would just have that extra term kind of dangling off the end there. Does the strategy resonate? Hopefully. Okay. All right. Yeah. Okay. Let me share this. Yes, sir.
What did you change all the other terms? Because then you know like x minus 1 squared for all the different terms. Like when you multiply by 2x plus 1 cubed x minus 1, so all the terms are going to have an extra x minus 1. Like a would now be 2x plus 1 over x minus 1. Right, x plus 1 cubed over x minus 1 and all that.
Yes. Yeah, that would happen. Yes. But now you want to allow for degree up to, because I added that extra term. Before, the degree of the bottom was 4. But adding that square on the x minus 1 made the degree of the bottom 5. So that the top would be allowed to be of degree up to 4. So it's okay that we get that extra term in there. Does that make sense? It's actually helpful that that's true. So hopefully these notes make sense now. Basically, if any linear term in the denominator of the form ax plus b raised to the power n, you just kind of crawl that thing up to the power n, 1 power at a time. Does that make sense? And you can handle each one of those summands individually just by doing a basic use substitution, or the first thing is basically logarithm. Yeah, that's how it goes. Okay, so that's how we handle linear terms. Now what do we need to know about? What about the squared terms? What about the quadratic terms, right? What about those quadratic terms? Well, same idea, except what? Well, so I'm just talking about the form here. Anything of the form ax squared plus bx plus c raised to the power n, you crawl that thing up, first power, second power, all the way up to whatever power of ax squared plus bx plus c to the n you have. But notice what's the difference? What's the difference with the numerators? It's not just like a number, it's ax plus b. The why? Why does it make sense that it would be of degree 1? Because what? Because the bottom is of degree 2. So I have to allow for the potential of having degree 1 less than that upstairs. Does that make sense? Okay. So this gets a little bit uncomfortable at times, right? Because now the algebra becomes a little bit more challenging. Okay. But that's the basic strategy. I have some stuff written right here. It says, set your decomposition with a's, b's, c's equal to the original function. Multiply both sides by the denominator of the original function. That's the clear denominator thing I've been talking about, which is basically like you going re-adding the fractions, if you think about it for a few seconds, yes? Okay, and then what? Using convenient values of x or equating coefficients of like terms, solve for the unknown constants. That is the entire strategy. Yeah, that's it. Convenient values of x, that's the plug-in method, right? And equating coefficients of like terms, that's the comparing coefficients method. So you have both of these tools in your toolbox and you use them simultaneously to your advantage. Of course, the plugging in of stuff is typically a quick and easy way to get some of the unknown numbers. But the equating coefficients thing is also useful. Okay? Questions on that? We'll do some more examples of involving quadratic terms tomorrow, but I just want to make sure we're clear on this. So any questions at all? So hey, I don't think anybody's in here. No. All right, cool. Okay, so take out a piece of paper. Okay, and when you're done, you're done. You can just kind of flip it over in front of you and leave it there and go to lunch.